Hello friends, wishing you all a very good afternoon. I hope all of you are fine, doing
Hello.
good. Can you hear me better?
Yes, sir.
Great. So today we'll start with magnetic effects of current. Today I think JEE Main result has also come, right? Do you know? Do you have any idea about it?
Yes, sir. Result came.
So how was the result, beta?
Not good, sir. 30,000.
30,000. Doesn't matter. It's okay.
Sir.
Don't worry. See, you don't have to take anything seriously. No one exam can decide what you are going to do. Even if it's 30,000 rank you got, I think you are still you'll be still appearing for JEE Advanced, right? When is the JEE Advanced this thing happening?
Third. Third.
Third, 3rd of October, right? That's the exam.
Yes, sir.
When are you
Yes,
going to
sir.
register yourself then?
And today or tomorrow, sir.
Okay, from tomorrow
Yes.
onwards. So get ready for this. What about the others? Um, what about the other results? I mean, there are other students in the class as well. Sushil Ram, Praveena, Jyoti, Lata, Vishnu. What about you guys? Did you get your marks? Well, one of my students, I told you about him. His rank got in the late hundreds, so it's around 780. He has got one of my students all online, and they are not able to check their marks, so I'm getting results. So out of the 20-25 students that I taught online this year, around 17, 18 have got ranks, and the rest 8, 7, 8 are still looking for the results. So they'll get selected somewhere around 1,000, 10,000, 5,000. They'll get. Anyways, doesn't matter. See, what matters is what you are doing at this point in time. Magnetic effect of current is what we are supposed to do today in today's class. Okay. Now, what do you mean by this magnetic effects of current? Simple, if you have a current carrying wire and if you bring a magnetic compass close to it, it was observed that this current carrying wire um, creates a magnetic field and the compass started to reflect. This experiment was conducted by Orsted, and from there we found out that a current carrying wire produces magnetic field. In fact, a charge, if the charge is at rest, then it produces what? If the charge is at rest, depends. If you see a charge at rest, what does it produce? It produces electrostatic field. Did I tell you about this?
Yes, sir.
If the charge is in uniform motion, it produces electrostatic as well as magnetic
Magnetic field.
field. And if the charge is in acceleration, it produces EM waves. Now, basically, whether a charge is at rest or whether a charge is in motion, uniform motion, or whether a charge is accelerating, it also depends on your reference frame. So basically, what you see, whether it's electrostatic field or a magnetic field or an electromagnetic wave, actually depends on your reference frame. So that is why this branch is known as electromagnetism, and this field is known as electromagnetic field and electromagnetic force, EMF, for field as well as for force. You must have also heard about Lorentz force. Have you heard about Lorentz force? Lorentz force is given by Q into E plus Q V cross B. Do you remember this Lorentz force?
Yes, sir.
Now, so basically, if you see an electric field and you don't see a magnetic field, the force on the charged particle will be Q into E. If you see a magnetic field and you don't see electric field charge, the force on the charge would be Q into V cross B. If you see both, then you have both. And the most difficult problems that come in your JEE are of the case where you have both electric and magnetic field. The famous problem of that cycloid. Do you know that cycloid wala problem? Where you have a charge kept at rest and then you have fields, magnetic field and electric field. And then this is a question given in SC Verma. Then you have to find out what is the trajectory of this particle. It's a cycloid. Do you know what the cycloidal trajectory? Any idea about cycloidal trajectory? What do you call the cycloidal trajectory? Anyone? No? Is the trajectory of a point on the rim of a cycle. You have a cyclic tire. Now the cyclic tire, you make one point on the cyclic tire. Point A. Now what happens with the cyclic tire? It moves with a velocity v forward. It's in pure rolling. It also rotates with a velocity v by r. It's not like solenoid, beta. It's not like solenoid. Solenoid is different. Solenoid is just like this. Cycloidal. Call it cycloidal. Are you getting confused with that trajectory where I have a particle thrown at an angle? What is that trajectory? When I throw the particle at an angle to the magnetic field, the angle between magnetic field and B is theta. What is that trajectory that particle follows? Are you confused with that trajectory? What is the name of this trajectory? Is it cycloidal? If I project a particle, helical, yes, Sushil, that is helical. Helical trajectory. So there are different types of trajectory. Helical trajectory, cycloidal trajectory, elliptical trajectory. Planets move around sun in elliptical trajectory. There are different types of trajectory. Cycloidal trajectory, the trajectory of a point on the rim of a cycle. And I can make you find out that trajectory very simply. For example, we are just deviating from the main topic, but see, this is road. This is a point on the rim of the cycle. Right now it is at the lowest point. Now, how does this cyclical tire move? It moves with a velocity v. It also rotates with an angular velocity v by r. Yes or no? Yes or no? After time t seconds, if I say that time starts here at time t is equal to 0, this is the time t is equal to 0. Can you tell me what is the x coordinate and the y coordinate of the point A as a function of time? The path this particle follows is known as a cycloidal path of a point on the rim of a cyclic tire. It's known as a cycloidal path. Think about it. How do you find it? What I was telling you was, this is the most difficult question that comes in a paper where you have both electric field and magnetic field. There are different ways in which electric and magnetic field can be there. This is the most difficult way of having an electric and magnetic field, that you have a cycloidal path. That's the question given in SE1, probably we will solve it, don't worry. But given that I have given you a velocity v and angular velocity v by r, can you tell me the x and y coordinate? If I just say that the particle starts its motion from this point and your x is 0 and y is 0, can you tell me the x and y coordinate of this particle as a function of time? This is not a question of electro, this is a question of mechanics from chapter 1. How will you find out the x and y coordinate? You can find out the x and y coordinate, you would be able to find out the x and y component of velocity. So the entire question will be find out x, find out y, find out vx, and find out vy. Can you do that for me? You can do that. That means you have a fair idea about what we are talking here. Okay, let me go back and let us go back to magnetic field. So if I have a charge moving with a uniform velocity, which is nothing but the current. When you have wire in a current, all the particles or charged particles are moving with something known as the drift velocity, the uniform velocity motion. They will create something which is known as magnetic field. And when we understood that magnetic field is also created by charges, we combine the two branches. Maxwell combined the two branches and call it electromagnetic field or electromagnetic force, and the branch became electromagnetism. Now, how do we study this branch? Now, to study this branch, because this is known as magnetic effect of current, what do? We go on to magnets. Now this part is not in your JEE Advanced, so I'll just go through magnets as two poles, North Pole and South Pole. A monopole magnet is not possible. Every magnet has its pole strength. I hope you understand this pole strength. And every magnet has a pole length, magnetic length, and geometrical length. Geometrical length is the end-to-end length. Magnetic length is the distance between the north and the south pole. Every magnet creates a magnetic field, and every magnet is determined by a letter known as magnetic dipole moment. This is the magnetic pole strength. Every magnet is determined by a magnetic dipole moment. Do you know magnetic dipole moment? This magnetic dipole moment is same as what we have electric dipole moment. So whatever formulae you see here are similar to the formulae that we did for electric dipole. The only difference is here you have mu naught by 4 pi. Here you have mu naught by 4 pi. There you had 1 by 4 pi epsilon naught. Now this is again one thing that you must remember. Wherever mu naught appears in the numerator, epsilon naught appears in the denominator, and vice versa. Wherever epsilon naught comes in the numerator, mu naught will come in the denominator. Why is that so? Why are this mu naught and epsilon naught related like this? Is there any relation between them? Does anyone know this? Between mu naught and epsilon naught? So whatever formula you are studying here, you are looking at here for a magnetic dipole, the same formula becomes true for electric dipole. Mu naught by 4 pi gets replaced by 1 by 4 pi epsilon naught. In fact, 4 pi are still same. The only thing that is getting replaced is mu naught is in the numerator and epsilon naught is in the denominator. That is all that has changed. Instead of this magnetic dipole moment M, you have electric dipole moment P. Magnetic dipole moment is M into 2L. M is the magnetic pole strength. Electric dipole moment is Q into 2L. Do we understand this? So the same formula are coming here. If you have not read this formula, you can have a look at it again. Magnetic lines of force of a bar magnet, we all know this. Now remember, there is a difference between electric field and magnetic field lines. What is the difference? The one major difference is electric field lines are in open loops. Do you know this open loops? Electric field lines are in open loops. What do you mean by this? They have a starting point, they have an end point. They start from a positive charge and they end on a negative charge like this. They have a starting point, they have an end point. Starting point is positive charge, end point is negative charge. The other way of saying this thing is that electric monopoles exist. You can have a single positive charge, it can have existence. You can have a single negative charge, it also has existence. But a magnet always comes in pairs. A magnet always has two poles, north and south. Outside the magnet, magnetic field lines are going from north to south. Inside the magnet, the magnetic field lines are going from south to north, and hence they are in closed loop. Do we understand this? Do we understand this? Can I have raised hands? Now, we had seen the force of attraction or repulsion or force between two electric dipoles. Similarly, you have force between two magnetic dipoles, and if you see, the formulae are exactly similar. The formulae are exactly similar. Mu naught in the numerator, epsilon naught in the denominator. That is the only change. M1, M2 are getting replaced by P1 and P2. The formula remains exactly same. You may find it difficult to understand it in terms of electric dipole, but in case of magnetic dipole, it becomes more clear. Can I have some reason that we understand this? So far, so good. Electric dipole, magnetic dipole, both are the same sort of things, same sort of terms. Do we understand this?
Yes, sir.
Okay. Then you remember one electric dipole was kept like this, one electric dipole was kept like this. And what was the force between these two dipoles? I'd already given you this. This is again the same question in the form of magnetic field. So I have again given you in the form of magnetic field. Remember, same question comes in the magnetic field as an electric field. Magnet in a uniform magnetic field, whether it's a magnet or it's a current carrying loop. Current carrying loop also has a magnetic dipole moment given by NIA. The similar formula for electric dipole in electric field, P cross E, magnetic dipole, magnet in a field, M cross B, current carrying loop in a magnetic field, M cross B. The only thing is M is the magnetic dipole moment of the loop, NIA. In the second case, it is magnetic dipole moment of the magnet, M into 2L. In the third case, it is electric dipole moment of the electric dipole, Q into 2L. And electric field there, magnetic field here, everything else remains same. Similarly, it is the formula for energy in a magnetic field. If it is a magnetic dipole, it is minus mp cos theta. If it is an electric dipole, it is minus pe cos theta. Do we remember this? Similar question here. We had seen a question where there was a case of finding out the time period. If you rotate it, if you just disturb it from a stable equilibrium occurs when theta is 0 degree. The angle between magnetic dipole moment and magnetic field is 0 degree. That is stable equilibrium. If you rotate it from that, we'll again come back to stable equilibrium. Time period we are already discussed. Yes or no? Can we move further?
Yes, sir.
See, this is example number 6. Same question we had done for electric dipole. The same question they have made for magnetic dipole. In this case, it is a magnet. The same question could be made for a current carrying loop. You have a current carrying loop kept like this. You don't have to keep it like this. You will keep it like this because current carrying loop ka area vector goes perpendicular to that. Remember, you don't think about the current carrying loop. You always think about the magnetic dipole moment M vector. Are you getting my point, everyone? See where is the direction of the magnetic dipole moment M, which is NIA vector for a magnetic loop, current carrying loop. Now, a magnet of magnetic dipole moment instead of magnet of magnetic dipole moment, it will become a current carrying loop, is released in uniform magnetic field of induction. In this figure, what is the kinetic energy? What is the maximum kinetic energy? Will it perform SHM? Same question could be asked for electric dipole. So you can think it of as a question for electric dipole. I think we had discussed the same question in electric dipole. Yes or no? We also found out the angular acceleration of this dipole. Do you remember that question? Yes or no?
Yes, sir.
Okay. The same question could be done here. Remember, all the three cases are exactly same. Now, as I told you, Orsted found out whenever there is a current carrying wire, it produces magnetic field. All know this Orsted experiment. We can straight away jump on to this one from Orsted experiment. From this Orsted experiment, you might not have seen this equation. Magnetic field created by a point charge. Do you know this formula? Magnetic field created by a point charge. Did you go through this formula? Magnetic field created by a point charge. Yes or no? If yes, good. If no, don't worry. You can now have a look at this formula. This is the magnetic field due to a point charge. If you can see, there's a positive charge. There's a point charge here moving with a velocity v like this. You have to find the magnetic field at point P. R vector is a vector joining the point charge to the point P. Theta is the angle between them. This is the scalar equation of this magnetic field, which only gives me the magnitude. You can find out the direction using right hand thumb rule. You remember right hand thumb rule? You do V cross R, V cross R, and the fingers will give you the direction of the cross product. Do you remember this?
Yes, sir.
Instead of this scalar equation, you can also use this vector equation, convert everything into vectors. If the charge is positive, put it as positive. If the charge is negative, put it as negative. You will get the value of magnetic field here. But here, you always put the charge as positive. You always put the charge as positive in the scalar equation, because scalar equation only gives you the magnitude. Magnitude can never be negative, it is always positive. You always put the positive value in magnetic field due to a point charge if you are using the scalar equation. Direction, how do you find the direction for a negative charge? There is no way of finding the direction for a negative charge. You find the direction for a positive charge, reverse it. That will be the direction of magnetic field created by a negative charge. Am I clear?
Yes, sir.
Now, from this charge, if you have a large number of charges flowing in a wire, it becomes the magnetic field due to a current carrying wire. The Biot-Savart law gives us the magnitude of the magnetic field due to a small length dl of this wire. The small length dl is always sometimes known as the current carrying element, dl. This dl is treated as a vector quantity. The direction of this dl is the direction of current, and the length of this dl is the magnitude of dl. So this becomes the magnetic field created by a small segment dl, mu naught by 4 pi I dl sine theta by r square. This is the scalar equation. You put dl cross r to find the value of dl cross r using right hand thumb rule, and that will give you the direction of magnetic field created by this small element. I hope you remember this formula. Then you can also have the vector formula. The vector formula for this current carrying wire, everything has to be converted into vectors. R becomes the position vector of test point with respect to dl. To find the entire magnetic field for the entire wire, you will have to integrate these small fields. Remember, whenever you are integrating fields, electric fields or magnetic field, always think about the direction. Always keep the direction in your mind. You miss that direction wala part, you will always suffer and your answers will always be wrong. Then using this principle, we are not going into deriving the formula for a straight wire. I hope you have seen this formula. If you have a straight wire carrying current I, and you have to find magnetic field at the point A, you call one angle as theta 1, other angle as theta 2. R is the perpendicular distance between the wire, straight wire, and the point. The magnetic field is given by mu naught I by 4 pi r sine theta 1 plus sine theta 2. Yes or no?
Yes.
How do we find out the direction of this? You can simply do dl cross r. If you find problem in doing dl cross r, you can simply consider it as I cross r. You put your thumb in the direction of r, I. You move your fingers in the direction of r, and then you curl your fingers, and that will give you the direction of magnetic field. Yes or no? We understand this, everyone?
Yes, sir.
Okay. And here, as you can see, they have given, using the right hand thumb rule, the magnetic field at different points. As you can see, on the right hand side of the wire, you have magnetic field which is going in. On the left hand side of the wire, you see magnetic field which is coming out. At point C and at point D, which lies straight ahead or behind the wire, the angle is 0 or 180 degrees, and hence the magnetic field at these points become a 0. I hope you understand this. Yes or no?
Yes.
Now, sometimes you can have a point behind the wire, so you can call one of the angles as theta 1. You can call one of the angles as theta 2. In this case, the magnetic field becomes sine of theta 2 minus sine of theta 1. I told you how to do this. I told you that when I am doing this, I am using the superposition principle. So I assume that this wire, I assume that this wire starts from here, then I superimpose another wire carrying current in the opposite direction, and I do superimpose the two fields. No matter how you do it, you will always end up with this answer. Yes or no? This is the magnetic field created by a straight wire. Once you know this standard formula, which is here, you can use this standard formula to find a magnetic field due to any type of configuration. For example, if it is an infinite wire, theta 1 and theta 2 becomes 90 degrees. So 1 plus 1 becomes 2, and the answer is mu naught I by 2 pi r. Yes or no?
Yes, sir.
If one angle is 0 and the other angle is 90 degrees, that is semi-infinite wire, the answer becomes mu naught I by 4 pi r. Yes or no?
Yes. Yes,
So
sir.
we all know this. I'll just give you a small question to discuss so that you are ready with this. Find the resultant field at the point C. I think this is a rectangular diagram. And what is the magnetic field at point C? Just give me your thoughts. How will you find it out?
Sir, due to each.
Due to each. How will you find out due to each? You don't have to find out due to each. Find out the magnetic field due to this wire. Multiplied by 2, you will get the magnetic field due to this wire as well. Yes or no? Both the fields are going in the same direction. Yes or no? In fact, all the fields are going in the same direction. What is the direction?
Yes, sir.
Inside,
Downwards.
inside, not downwards, inside, into the plane. Into the plane is inside. So you find out the magnetic field to this wire. How will you find it out? You join this point, you join this point, then you draw a perpendicular, then you find out these two angles, then you find out the value of this. It is a by 2. It's very simple. Yes or no?
Yes, sir.
How do you find out the magnetic field to the other two wires? Join here, join here, join here, find these two angles, find the value of this thing, put the formula, get your answer, stay happy. Is everyone getting this? Yes or no?
Yes, sir.
Now there is a very peculiar case that comes here in this diagram. As you can see, a current carrying wire is coming from infinity and again going back to infinity, and then it is getting distributed. We are supposed to find out the magnetic field at point O. How will you find it out? How will you find this one out? Remember, remember, if all these wires are same means they are symmetrical with respect to the central point. Now what will happen when the current comes? Current will get divided in these two branch number 1, branch number 2. Now the length of this wire is proportional to their resistances. No, sorry. The distance of this wire is proportional to their length, and similarly current will be inversely proportional to their resistances. Current will divide. In the larger part, less current will go. In the smaller part, more current will go. But what will happen? The smaller part will have small angle, larger part will have large angle. So effectively what will happen is, whatever magnetic field this portion is creating, the blue one, same magnetic field will be created by the niche wala portion, the orange one, and they will cancel each other out. Because one will create field in the outward direction, the other will create field in the inward direction. These two wires, they are pointing towards the central point. So the field created by these two wires will also be 0, and hence the answer will become 0. Do we understand this?
Yes, sir.
I hope you have seen questions of this nature. I will again, from my end, I will again give you examples of this. For example, if you had a question like this, ting, 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 and ting. And let us say this is the center. I hope you understand. This is the center, and this current is coming from here and it is going out from here. It is getting divided here and here. What is the magnetic field at the center of this coil? Center of this circle. You understand the diagram? Yes or no?
Yes, sir.
What is the magnetic field at the center of this? If you have not understood it, I'll make it in a better way. For example, this is my circle. Circle is enough. Now I have current coming from here, entering here. current entering here and current leaving from here. This is A, B, C, D, and this point is going to infinity. This point is going to infinity. Current is getting divided into two branches. ऊपर वाला branch is branch number 1, नीचे वाला branch is branch number 2. How will you find out the magnetic field at the center of this loop? Let us say the radius of the loop is R and current in the wire is I. What will be the magnetic field at the center of the loop O? Can anyone tell me? You will say, sir, tell us the angle. So I'll tell you one angle. This angle I don't need to tell you. Let me call this angle as 45 degrees. What is the magnetic field at the center? Are you getting the point? Now remember, in such questions, magnetic field created by this portion and magnetic field created by this portion. What will happen to the magnetic field created by these two portions? They will get cancelled. Magnetic field created by this portion also becomes 0 because point O lies behind this. The only thing you have to find out is the magnetic field due to this portion, and you can use the formula that sine theta 1 minus sine theta 2. Do you understand this?
Yes,
One
sir.
angle becomes 90 and the other angle becomes 45 here. You can do that formula. I hope you understand that formula. Every straight wire has to be done with that formula, sine theta 1 plus sine theta 2. In this case, the point is ahead, so you will superimpose one wire like this and you will put another wire in the ulta case. Find out the magnetic field to the total wire, subtract the field from here and you will get your answer, or sine theta 1 minus sine theta 2. Whatever way you prefer, you can do it in that way. Am I clear, beta? Yes or no?
Yes, sir. Yes, sir.
Any question that comes in this category, you should be able to do this. I hope you will be able to find out the answers for this one. Now, just for my knowledge, how will you do a question of this type? Similar question has come in one of the JEE. How will you do a question of this type? I have two wires here, wire 1, wire 2. One wire magnetic current is coming out, wire 1, one wire current is going in. Both are infinite wires. You have to find the magnetic field at point P. How will you do it? Very simple. I think most of you will know it. Magnetic field due to this wire will be mu naught I by 4 pi r into sine theta 1 plus sine theta 2. Both angles are 90 degrees. Remember, this r must be the distance between the perpendicular distance between the point, between the wire and the point. In this case, the distance is 2a. Do we understand this? Yes or no?
Yes, sir.
Remember, beta, if I talk about wire A, just see this. If we talk about wire A, current is coming out. Now, if I draw the magnetic field to this wire, remember this magnetic field will be moving in circles. Yes or no? So magnetic field will be moving in a circle like this. Magnetic field at this point will be going outwards. Yes or no?
Yes, sir.
If you look at the wire B, current is going in. Magnetic field due to this wire will be moving in circles like this. My circles may not be perfect, but they give you the direction of magnetic field. Yes or no? Both the fields are equal in magnitude because currents are same. So their horizontal components will get cancelled and their vertical components will get added up. Yes or no? Or if you don't
Yes, sir.
understand the horizontal and vertical components, you have two equal fields, V1 and V2, inclined to each other at an angle of 120 degrees. You can apply B1 square plus B2 square plus 2 times B1, B2 cos of 120, and you will also get your results. Yes or no?
Yes, sir. Yes.
Anyone has any doubts on this?
No.
Okay. Now this same principle can be applied to find out the magnetic field due to this sheet. This is a question I think that is taken from Irodo. This sheet carries a current I. The width of this sheet is given as W. Infinite sheet, obviously, you have to find. There are two types of questions that can be made here. The point P can be in the same plane. The point P can be like this. You can do both of the questions. No problem in doing all of these questions. They are pretty simple. If the point P is here, how do you do it? Any idea how do you do this? Anyone, any idea how do you do this? Very simple, beta. You just break it into patla wires. One such thin wire at a distance x. The length of this wire is dx. The current in this wire becomes mu naught I by w multiplied by dx. It is an infinite wire. So the magnetic field due to this wire becomes mu naught I की जगह di, mu naught into di divided by 2 pi x. Di is I by omega, yeah, w into dx. You integrate this from a to a plus omega or a plus w, and you get your answers. Yes or no?
Yes, sir.
Remember, all the fields are going in the same direction. Yes or no?
Yes, sir.
Okay. Then the next type of wire is a circular loop. What is the magnetic field due to a circular loop? You must be knowing its form and the general formula. So I hope you know this. What is the general formula for this? If I have a circular arc or a loop,
Mu naught I by 2R.
what is the general formula? If I have a circular loop like this, not entirely full, makes an angle theta, carries the
Theta
current
by
I,
350, sir. Into.
radius is r. What is the general formula? Mu naught I by 4 pi r multiplied by the angle theta. Remember, this theta must be in radians. Do we remember this? Yes or no?
Yes, sir.
If you do not remember this, please keep on noting this formula that I am giving you. The next one is magnetic field on the axis of the loop. The loop carries a current I. Remember, magnetic field ka direction. If the loop is carrying current like this, magnetic field go in this direction. If the loop is carrying current like this, magnetic field will go in this direction. Whether the point is on this side or other side does not change. Magnetic field always remains in the same direction. In this case, at this point, magnetic field is also here. At this point, magnetic field is also here. At this point, magnetic field is also in the same direction. And the value of magnetic field is this. You must be knowing this formula. When you put x as 0, magnetic field does not become 0. It becomes mu naught I by 2r. Do we remember this formula? Remember, n is also multiplied here. N is the number of turns in the loop. Do we remember this formula?
Yes, sir.
And This is the way magnetic field looks like. See, it is this way that it looks like. The magnetic field created by a ring. As you can see, it's coming from infinity this line and going to infinity this line. Getting my point?
Yes, sir.
And here, if you see the magnetic field due to this loop, it's just like the magnetic field due to a bar magnet. And hence this loop can be treated as a bar magnet. This bar magnet has a magnetic dipole moment, which is m multiplied by 2l. This loop has a magnetic dipole moment multiplied, which is given by NIA. Yes or no?
Yes, sir.
This loop has a north pole. This loop has a south pole. This bar magnet has a north pole. This bar magnet has a south pole. Similarly, this loop has a north pole and this loop also has a south pole. How do you find the north pole of this loop? How do you find the north pole of this loop? So you turn your fingers in the direction of current. You turn your fingers in the direction of current. Thumb is the north pole and this is the south pole. So in this case, this is north and this is south. Am I clear? Yes, no.
Yes, sir.
And that is why you might get this question: when do the loops attract each other and when do the loops repel each other? Do you understand? When do the loops attract each other? See, for this loop, this is north, this is south. For this loop, this is south, this is north. When they carry current in the same direction, they attract each other, buddy. Yes or no?
Yes, sir.
So this is the easiest way of understanding when do the loops attract and when do the loops repel. Yes or no?
Yes, sir.
These are simple questions. Find the magnetic field at the center. We will discuss it fast. Due to this, it will be 0. Due to this, it will be 0. You just have to find out the magnetic field to this semicircular part, mu naught I by 4 pi r multiplied by 180 degrees pi. That is the answer. To find out this, magnetic field, this will get cancelled. Due to this wire, it will be mu naught I by 4 pi r sin theta 1 plus sin theta 2. One angle is 0, other angle is 90. And this is mu naught I by 4 pi r multiplied by 2 multiplied by pi. Do you understand this? Yes or no?
Yes, sir.
Chalo. So you know all this. All these questions are taken from Irodo some way or the other. I hope you can solve all these questions. Yes or no?
Yes, sir.
This is one of my favorites. In my favorite question, what happens is this loop goes till infinity. So in my question goes like this, ting, 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 ting. Do you understand my question? This is
Yes,
how I
sir.
make my question. So what happens is it becomes a series, a log series. If I call this angle as theta, this becomes a log series. One will get plus, other will be minus, one will be plus, another will be minus, and so on. Do we understand this?
Yes, sir.
I hope you will be able to do this. Yes or no?
Yes, sir.
Okay. Then this gentleman is known as solenoid. Do you know this gentleman? This is loops of wire.
Yes, sir.
This is known as the axis of the solenoid. Normally, we only find the magnetic field on the axis of the solenoid. Yes or no? Do you know the general formula
Yes,
for
sir.
magnetic field on a solenoid? You may not know it. I'll tell you. I don't trust this formula. This formula is not good. How do I change this formula? I change this formula in this way. This is my solenoid. This is my solenoid. This is my axis. If you have to find the magnetic field at this point P, what do? I draw a perpendicular like this. Then I join the two ends of the solenoid with this. Then I call this angle as theta 1. Then I call this angle as theta 2. And then my formula becomes, look at the red formula, mu naught Ni by 2 into sine of theta 1 plus sine of theta 2. This is how I remember my general formula for magnetic field due to a solenoid. N standing for number of turns per unit length, I standing for current in the solenoid. Theta 1 and theta 2 are the angles that this point makes with one angle of the one end of the solenoid and the other end of the solenoid. Why did I write the formula in this way? Does this remind you of something?
Yes, sir. Due
This
to rod.
formula is similar to the formula of a
Right.
straight wire. Yes or no?
Yes, sir.
In the straight wire, we have mu naught by 4 pi r sine theta 1 plus sine theta 2 into I. Here you have mu naught by ni, mu naught ni by 2 into sine of theta 1 plus sine of theta 2. When this solenoid becomes infinite, both angles become 90. Your answer becomes mu naught ni. If you have to find the magnetic field here at one end of the solenoid, I call it semi-infinite solenoid. Some people call it end of an infinite solenoid. One angle becomes 0, other angle becomes 90. Answer becomes mu naught and I by 2. Do you understand this, or have I gone too fast?
Understood.
Okay. Ideal solenoid. Some people call it ideal solenoid. Ideal solenoid is an infinite solenoid, mu naught ni by 2, and the magnetic field at the end is mu naught. Ideal solenoid is infinite solenoid. Magnetic field is mu naught ni. At the end, magnetic field is mu naught ni by 2. I call it semi-infinite solenoid. These people call it end of the solenoid. If it is an infinite solenoid, it cannot have an end. Anyways, I cannot argue. Comparison between an ideal and real, just see the comparison. This is an ideal solenoid. At the center, the magnetic field is mu naught ni by 2. At the end, the field is mu naught ni by 2. At the center, the field is mu naught ni. But this is how the field of a real solenoid looks like. Am I clear?
Yes, sir.
Okay, then there are some questions given in this book, in this sheet. I have already sent you this sheet. Probably you will get this sheet, or it must be already there present in your what? You have an app, right? How are you getting the study material?
In group, sir.
Group. So
Some
probably
group, sir.
it will
My
be in your
ma'am will.
probably it will be in your group. I've already sent it before the class, so probably it will be in your group. In the next class, we'll start with this Ampere circuital law, and we'll try to wind it up and do. Even if you can do these questions that I have done, it is good enough for you right now. Or
Yes,
if you
sir.
want, I can send you another sheet for exercise, but I just don't want to burden you with all these questions, because even if you can do this much, revision is only this much better. Okay. Uh, if you want, I can give you 1,000, 5,000 questions. But if will this serve any purpose? That is the problem. Okay. So I'm just going through this. You must be having your own questions. Try those questions now. Even if you do whatever questions I have given you is more than enough. JEE is not so tough that you have to do all the questions in the universe at this point in time. You can only do this much. I'm sure if your rank is 30,000 in the JEE Mains, with this I can bring it up to at least under 10,000 if you do it correctly. Okay, if you do it correctly, I can get you somewhere around 10,000. I can't get you more inside because you're just too far away. Okay, so work on this. If you have anything that you want to ask me, you can ask me at any time. Okay, chalo, I'll wind up today's class. If you have any doubt, you can ask me. In the next class, we'll move ahead and we'll try to wind up. I'll spend more time on this because I think that if any question comes from this part, you should be able to do it. Else, it becomes very tough to score in physics. This is the most scoring part. Electromagnetism, thermodynamics, and modern physics and optics. These are the 4 topics that must be good. And some part of mechanics. You should be able to score in them. If you can't score in them, you will lose a lot of marks. Chalo, I'll wind up the class now.